So this is a review of homework 5, which is focused on the second hypothetical rule, which is negation introduction. Negation introduction. And this rule is also sometimes called reductio or reductio ad absurdum, which is Latin for reducing to absurdity. So this rule is actually just the same in terms of concept as the procedure that we created and followed for evaluating the validity of arguments in refutation or truth trees. So just to remind you of that, take a real simple example of a valid argument like if P then Q, P, therefore Q. So you'll remember that when we're doing a refutation tree, we negate the conclusion. So we add a negation to the conclusion, and then we look for contradictions. So if P then Q decomposes to not P or Q, discharge, and we get an X on both branches. And what that told us was that if we assert the premises and deny the conclusion, we create a contradictory set of sentences, which means a set of sentences that taken together are false under every possible interpretation. And that satisfied the basic definition of validity. A valid argument, you'll remember, is an argument in which it is impossible to have true premises and a false, i.e., a negated conclusion. So that's exactly what we exploit in the rule of negation introduction, except we're not doing trees, we're doing natural deduction. So the basic idea here is that if you take an assumption, the two assumptions, if P then Q and P, label them as assumptions. Now, of course, we know that we can just get Q directly by applying the rule of conditional elimination, so we're just using this as an example that's easy to follow. The rule of negation introduction tells us to hypothesize the negation of the conclusion. So since the conclusion is supposed to be Q, we hypothesize not Q, and you'll remember hypothesis requires us to indent. So then we know that if this is a valid argument, hypothesizing the negation of the conclusion creates a logically inconsistent set of sentences. And so that means from these set of sentences, we should be able to derive a contradiction. So that actually becomes our task. Our task now is to derive a contradiction. And that's very easy because now we do just apply conditional elimination to get Q, right? By 1, 2 conditional elimination. And now we have an explicit contradiction. But what the rule requires us to do, and this is extremely important, is it requires us to conjoin the two contradictory propositions. So what we have to do is we have to actually write Q and not Q, and that's just by 3, 4, conjunction, introduction. Okay, so we've derived a contradiction, we've stated it explicitly. Remember, a contradiction isn't just an atomic formula and its negation, it's any formula and its negation. So this is a conjunction between an atomic formula and its negation, but that's not a requirement of this rule, just like it wasn't a requirement with trees. Okay, and the last thing you have to understand about negation introduction is how to discharge the hypothesis. So what negation introduction tells us is it says, good, you've derived a contradiction after hypothesizing the negation of the conclusion. So on the next line, you get, and this has no correlate in the truth tree approach, you get to assert the negation of the hypothesis. Okay, and so what that actually means is that you write not whatever that hypothesis is. And in this case, the hypothesis is not Q. Okay, so don't get too clever and say that, well, that's just Q and write Q. That's not okay. You have to write not whatever the hypothesis happens to be, not Q, and you drop a line. Okay, and then you write, in this case, 3 through 5, negation, introduction. Okay, now if you had been told to demonstrate if P then Q, P therefore not Q, you would be done. But if you had been told to demonstrate or derive if P then Q, P therefore Q, you are not done, but of course you know how to get done now. All you do is write Q by 6 and negation, elimination. Okay, so that's how it works. It's very straightforward, especially since we were preceded by the refutation tree analogy, but partly because this has been preceded by a bunch of basic rules and the rule of conditional introduction, this is a point in the class where just because we've added so much power to the system now, things start to get complicated. So some of the proofs you encounter in the homework are quite a bit more challenging than anything you have encountered so far. So this homework review is going to be quite a bit longer, and you're really going to need to set aside quite a bit more time to get this under your belt than the previous homeworks. So the other thing that makes this complicated, or a little more complicated, is just that you are often going to be using negation introduction in conjunction with conditional introduction, and you're going to have to use your noodle and sometimes just guess and retry when it doesn't work to figure out which one to use. So let's look at number 1. I'm going to stay on the whiteboard for now. So number 1 says you're given if P then Q, just as one assumption, and you're told to prove if not Q, then not P. All right, so take on if P then Q as an assumption, and you're trying to prove this conditional. Now, if you're trigger happy and you've just learned negation introduction, you find yourself wanting to just negate, right? To start off with a negated conclusion, and at this point, that's usually a bad idea. So basically, this is pretty important. It's very important. Basically, you want to always do anything you can achieve by conditional introduction first. Okay? So you're trying to derive a conditional here. So forget about negation introduction for now and just go with conditional introduction and hypothesize not Q. Okay? So because we now have two different hypothetical rules, I'm going to go ahead, and this is not part of the formalism and it's not a requirement, but I'm going to usually make a notation as to why I'm creating this hypothesis. So I did this one for conditional introduction, and I'm just making a note right here for that. Okay, and then I got to figure out what to do. Now, I would prefer to just use everything at my disposal instead of negation introduction. So just think of negation introduction as the big hammer, right? And it's something you only pull out when you really need it. That's not strictly true. Sometimes using negation introduction makes things go faster, but it's really the most powerful method. And since it is the most powerful method, it also often involves more steps than other methods. So it's sort of best to hang around and see if you can do without it first. But here, we see that we can't, right? We got if P then Q and not Q, and we don't have right now any rule that allows us to write not P. You've had a little logic, so you know there is a rule that allows you to do that, but we don't have it in our system. It's called modus tollens, and we're going to get it in our system, but it's a derived rule in our system, and you know what we're doing right now is we're deriving it. So what am I going to do? Well, I am now trying to derive not P, okay? So what I'm going to assert is the negation of the conclusion for negated introduction. Now, up until now, you might think that that means that, just like with the trees, that you actually have to write not P, but that's not the case. Hypotheses are things that you can take on at any time you like for any reason you like. So the basic rule for hypothesis is hypothesize anything you want. You can't do any damage that way because you can't leave a hypothesis in the proof. A proof is not done until you've discharged all the hypotheses. So what I want to do in this case, and it's okay if you write not P, but I'm just going to write P because P is equivalent to not P. And this is going to shorten my proof a little if I do it this way. So this is just a hypothesis for negation introduction. So now I'm too deep, right? One was the hypothesis for conditional introduction. The other was the hypothesis for negation introduction. And now I'm just going to do a little logic, right? So now I'm going to, and this is going to look like before, I'm going to get Q by 1, 3, conditional introduction, and same as before. Now I'm going to write Q and not Q by 2 and 4, conjunction introduction, right? Sorry, I might have actually said conditional introduction on line 4, but of course it's conditional elimination. Let me make that explicit. Okay, so I have my contradiction, and now I can discharge. Remember, we always have to discharge our hypotheses in reverse order. So now I can discharge my hypothesis by writing not P, right? The negation of the hypothesis, that's always what you write. Drop a line, and that's 3 through 5. negation, introduction. Okay, and so now I've got not P, and now I'm back to my hypothesis for conditional introduction. So now you can see that I've got if not Q, then not P. So I'm going to discharge that hypothesis. If not Q, then not P. And that gives us 2 through 6, conditional introduction, and we're done. Okay, so this is a nice simple example where we have proved the rule of modus tollens. We won't, at this point, use it. We won't use it until we actually introduce a bunch of derived rules in the next section. But this is a rule that we proved by taking advantage of both of our hypothetical rules. So really nice demonstration of that. Okay, so problem number 2 tells us to derive from the assumption P and Q that it's not the case that if P, then not Q. Okay, so here, of course, the main operator is what? It's this negation. So there is no opportunity here to begin with the conditional introduction because the conditional is not the main operator. So in this case, it really looks like the best way to begin is with a negation introduction. Well, what you might want to do before that is to go ahead and separate these, just because you can, right? So 1 and conjunction elimination, 1 and conjunction elimination, and that gives you these free and clear outside of any hypothesis that might ultimately get locked up. You don't need to do this. I don't always do it. The upside to doing it is what I just said. It gives them to you free and clear. The downside is that sometimes you will find that you didn't have to do this, so it might make the proof longer. In other words, maybe you only need the P or only need the Q, etc. Anyway, that's really totally up to you. Nothing bad happens by doing it or failing to do it. Irremediably bad anyway. Okay, so now let's go ahead and see what happens when we hypothesize, in this case, the negation or the opposite. Opposite is, by the way, not a concept in logic. Sometimes they say the opposite, but it's not a technically defined term, okay? It's just easier than to say the proposition with the opposite truth value or something like that. So hypothesize if P, then not Q, for hypothesis 4, negation introduction. And again, just do a little logic. We're going to get not Q this time by 2, 4, conditional elimination. Once again, we have a straightforward contradiction, Q and not Q, by 3, 5, conjunction introduction. Got our contradiction, which means we now can discharge the hypothesis and negate that hypothesis. Not if P, then not Q. Notice the importance of adding the parentheses in, right? Both to achieve our result, and also because if we just negated the P, we would not be negating the hypothesis, we'd be negating P. All right, drop a line, 4 through 6, negation introduction, and you're done. All right? All right, so the next one gives us two premises, P and Q, then R or S, and it's not the case. Not the case that R or S, and we're supposed to derive, it's not the case that P and Q. Now that you've seen a couple, you should be definitely stopping and doing these on your own unless you've already done it well and are just checking up on things. Okay, so like before, you've got a conjunction that's been locked up by a negation, and that's what negation introduction is pretty much built for. So we're going to go ahead and hypothesize P and Q, and I'm going to make a note that that's for negation introduction. And then I see, right, immediately that I can get R or S by 1,3 conditional elimination. And the point of this proof is to get you to recognize when you've got a contradiction that's not a contradiction between atomic propositions. So now you've actually got R or S on line 4, and it's not the case that R or S. You've got to see that, or you're never going to get this proof, right? So all you have to do is write, it's not the case that R or S and, right, R or S by 2,4 conjunction introduction, and then you're home free, right? Now you just have to write not, right? The negation, oops, see I made a little, oh no, that's fine. Sorry, not, just not, right? Not P and Q. The negation of the hypothesis, 3 through 5 negation introduction, and that's all there is to it, right? So that was problem number 3 here. Okay, so you might feel like you're getting in a little bit of a groove now. I hope so, but this problem might throw you out of it just a tiny bit. So P, not S, or not P, if P then R, and we're supposed to show not S and R, okay? So again, keep your negation introduction in your holster and remember the other things that we often have to do. One very important thing to understand here, and I haven't said this before, so pay close attention. I mean, I haven't said it in this homework review before, is that if you have a disjunction as an assumption, before you even think about negation introduction, you should be thinking about disjunction elimination, okay? So the problem is this: if you begin by negating your negating your conclusion, and then you realize that you're involved in a disjunction elimination, then you're going to have to prove conditionals, right, that give you, as a consequence, a proposition that's the negation of that negated hypothesis. Typically, that's how you're going to do it, and that's not typically going to be that easy. So the best thing to do is just bite the bullet and say, okay, I'm going to do a negation, a disjunction elimination. So you can hashtag out over here. I'm going to show, first of all, if not S, then not S and R, right? And then I'm going to show if not P, then not S and R. And then you tell yourself, if I need conditional introduction, which you definitely will, I'll use that. And then if I need negation introduction, I'll use that within the context of these two derivations. Okay? So what you're going to do is hypothesize for conditional introduction, not S. And of course, now what you're just trying to do is get not S and R, but 1 and 3 gives you R, right? So you've got R by 1, 3 conditional elimination. And so now you've got not S and R by 4, 5 conjunction introduction. And you've completed your first conditional. So if not S, then not S and R, right? By 4 through 6 conditional introduction. So notice you didn't even need negation introduction. And if you don't need it, you really don't want to be using it because it makes the proof longer and harder to follow. But that's just the first leg. The second leg is going to be hypothesize for conditional introduction, not P, right? And again, you want to derive not S and R. Now, if you inspect your availables, you'll see that P is an assumption, right? So you've got a contradiction, P and not P. Now, calm down, because you can't just go, oh, P and not P, because you are not right now involved in negation introduction, right? So you got to get yourself involved in one first. So you're going to hypothesize the negation of what you're trying to prove, which in this case is it's not the case that not S and R. So hypothesize for negation introduction, okay? And now you just bring down your P and not P. By 1, 8 conjunction introduction, right? So this one probably feels really weird to you, and the way that I would describe the weirdness is this. Your hypothesis for negation introduction right here didn't have anything to do with generating P and not P, right? And that just feels wrong. It feels like what's supposed to happen is that the hypothesis generates the contradiction, but that's not a requirement, okay? It's an easily and intuitively made assumption that just turns out not to be the case. All you need is a contradiction. Any contradiction in a storm will work. So we have our contradiction, P and not P. And so now we can write the negation of the hypothesis, which is not S and R, right? So we have 9 through 10, negation introduction. And we don't want not S and R, we just want plain old not S and R, right? Which we have now through 11, and negation elimination, right? So we still got this hypothesis because remember we're trying to prove this conditional. So now we get to discharge it. If not P, then not S and R, right? Drop a line, and that's 8 through 12 conditional introduction. Okay, so this turned out to be a disjunction elimination proof, one leg of which just involved a conditional introduction, the other leg of which involved conditional introduction with a little help from negation introduction. And of course, we're not done yet. We still need to do write down our conclusion, not S and R. And on the basis of what? On the basis of 2, 7, and 13, right? So 2, 7, 13, disjunction elimination. Okay, so you're going to get tired of hearing me say this, but most people need to hear it. If you followed this proof and feel like you understand it, you don't, right? You don't understand it until you shut down the video and do it again on your own flawlessly. And if you have trouble, you got to come back, figure out what your mistake is, and then don't say, oh, now I understand it. Go back and do it again until you've created on your own every single one of these proofs on this homework on your own. You are not going to be in a position to do well, okay? It's really going to take work, and you've got to get to where you have mastered all of these problems before you let yourself move on. Okay, so the next one tells us to derive from this disjunction, not P or not R, the formula. It's not the case that P and R. It's fun to look and see what we're actually doing here. If you think about the refutation tree rules, the reverse of this is something we've been depending on. It's not the case that P and R, a negated conjunction, went to branching formula, not P or not R. This is going the other way. And what we're doing here is just proving one direction of an equivalence that we will introduce later, and it's called De Morgan's rules. Anyway, you should definitely try this on your own. What you need to do is just apply what we were talking about last time with respect to the strategy. And it's even clearer here, right? Because you've only got one assumption and it's a disjunction. So don't just jump in to negation introduction, jump into disjunction elimination. Right, so hopefully you've tried that, and let's see what, if it's anything like what we've got here. So on line 2, I'm going to, well, what I'm going to do is I'm going to, out here, tell myself, remind myself that I want to show, right, if not P, then it's not the case that P and R. And they also want to show if not R, then it's not the case that P and R for or elimination, disjunction elimination. So I'm going to hypothesize not P, right? And then seeing that there's nothing for me to do on the basis of that hypothesis, remember this was for conditional introduction, I'll go ahead and hypothesize the negation of the conclusion or its logical equivalent, which in this case would be P and R. Right, so hypothesis for negation introduction. I immediately see that I can get P by 3 and conjunction elimination, and that gives me P and not P by 2, 4, conjunction introduction. And so now I can discharge the negation introduction hypothesis. It's not the case that P and R, right? Drop a line, that's 3 through 5, negation introduction. And of course, what we were trying to prove is the conditional, if not P, then it's not the case that P and R by 2 through 6, conditional introduction. If I want, I can go ahead and scratch that one off my list. And now you can see pretty much the same thing's going to play out, right? But only with not R. So see if you can go ahead and finish this proof up. Come back and see if you did it right. So hypothesize not R. Hypothesis for conditional introduction. Once again, right, we will hypothesize P and R. You might be thinking, well, that's a lot of work. Why couldn't we have just done it once? Well, it just doesn't work. So that's my hypothesis once again for negation introduction. And then, again, I see a contradiction, R, 9, and conjunction elimination, and R and not R by 8, 10, conjunction introduction. Got my contradictions, so now I can assert once again it's not the case that P and R. Got a little bit sloppy here. Let me fix this. It doesn't look like I indented very much on number 9. Make the indent a little more obvious. Okay, so it's not the case that P and R. Drop a line, 9 through 11, negation introduction. And then just as before, right, we have if not R, then it's not the case that P and R by 8 through 12, conditional introduction, and that was our second conditional, so we're done with that. So now we just have to finish it off with an or elimination, disjunction elimination move, and we get to assert free and clear that it's not the case that P and R, right? And why? Well, because we have this disjunction and these two conditionals which we created, 1, 7, and 13, disjunction elimination. All right, so the next one gives us 3 assumptions. Another one containing a disjunction. Conditional if P then R, and not R as an assumption. We're supposed to derive a simple conclusion, Q. You know how to do it, right? Disjunction elimination. So if you haven't done it, do it. Come back, see if you did it right. I'm going to hypothesize P in order to show if P then Q, show if P then Q, and then later I'm going to show if Q then Q, which is not very challenging. So how am I going to show if P then Q? Well, 2, 4 gives me R, right? So 2, 4, conjunction elimination. That gives me my contradiction. So I'll just write R and not R by 3, 5, conjunction introduction. Are you getting this? Are you following this? Well, if you are, then you should be saying, wait, that's not right. What mistake did I make here? Right, I haven't made a hypothesis for negation introduction, so this is not going to help me at all. Now, I could just go ahead and make it here, right? I don't have to erase this, because I could, if I wanted to, just write R and not R all over again by conjunction introduction. There's nothing but an aesthetic objection to doing something like that, but I don't want to make this icky, so I'm going to go back, right, and think more properly. Okay, I've got my R, right, but what I'm really looking for is Q, right, and I don't see any way to get Q, So I do see a contradiction, so I'm going to hypothesize, right, for negation introduction. Remember, this was for conditional introduction. I'm going to hypothesize not Q, right? Then, right, I go ahead and assert my contradiction, R and not R, right? So 3, 5, conjunction, introduction. That allows me to discharge my hypothesis, negating the hypothesis. Okay, so not Q. 6 through 7, negation, introduction. But as before, I don't want not Q. I want Q. So 8, negation, elimination. And then I can go ahead and assert if P, then Q. By 4 through 9, conditional elimination. Okay, you might have been wondering, well, what if I had just on 9, right, so alternate reality, what if on line 9 I had just written if P then not Q and discharge the hypothesis there, right, by 4 through 8, conditional introduction, and then afterwards written, just changed it to if P then Q. Wouldn't that have been okay? And hopefully you know the answer to that. The answer to that is no, because you always have to be operating on the main operator. Okay, so there is no inference rule that's going to let you go from if P then not Q to if P then Q. This is hugely important to understand. When we're using inference rules, you always have to be working on the main operator. And that's going to change later when we use what we call equivalences, but we don't have equivalences yet, so we're constrained to this. Okay, so let's get this out of our sight. Make sure we don't do this sort of thing ever. So remind ourselves where we were here, right? We showed if P then Q. Why? Well, because we have this little project here. We just completed the first part. Second part is dead simple. Nothing easier than showing if Q then Q, right? Hypothesis Q. 12, if Q then Q. 11 through 11, conditional introduction. Done, except we haven't actually done our disjunction elimination. So let's just do a little bookkeeping. Here's our disjunction, right? Here's our first conditional. Here's our second conditional. So we can now assert Q by 1, 10, 12. Disjunction elimination. Remember, cite the disjunction first and then the conditionals in the order in which we created them. Okay, the next one requires us to derive a conditional if P then not Q from a disjunction, not Q or not P. So in this case, because the conclusion is conditional, that's what you want to simplify first. Always simplify your project by taking on as many conditional introductions as you can in a row. What I mean by that, just to be clear, is if the conclusion we were supposed to prove were if P then if R then not Q, you'd want to begin with two hypotheses, right? First, hypothesize P, and then immediately after, hypothesize R. You want conditional introduction to be your best buddy, right? Don't think of it as something that makes things more difficult because you've got all these hypotheses to manage. Think of it as something that makes things easier because instead of having to prove something long, you only have to prove something short and then just discharge a bunch of hypotheses, which is trivial. So what do you want to do here? Well, hypothesize P for conditional introduction, and then you have another disjunction elimination project. So you're going to show, right? Show if not Q, then not Q. Again, completely trivial. And show if not P, then not Q. Okay, this one's very straightforward. Go ahead and stop if you haven't already. Crank this one out. All right, so I've hypothesized P. I want not Q. First, I'm going to show if not Q, then not Q, which is trivial. Not Q hypothesis, right? That's if not Q, then not Q by 3 through 3 conditional introduction. That's out of the way. Now I'm going to hypothesize not P. And again, what I'm trying to get is not Q. I see no way of getting not P directly, right? Not Q directly, but I do see that there's a contradiction between my initial hypothesis and not P. So what I'll just do is hypothesize the opposite of not Q, which is Q. I could do not Q if I like. It'll still work out, just one extra step, right? So Q is my hypothesis. I did a bad job indenting that. Okay, so I've hypothesized Q this time for negation introduction. Before it was for conditional introduction. Once again, I'm just going to bring down P and not P, 2 through 5. Whoa, what am I saying? 2 and 5, right? 2, 5, conjunction introduction. Okay, so 2, 5, conjunction introduction, P and not P. We've got our contradiction. So now we can assert the negation of our hypothesis, not Q. And that's 6 through 7, negation introduction. And that allows us to assert the conditional we're working on. If not P, then not Q. Yep, that's an ugly line. And that's by 5 through 8. Conditional introduction, right? So we got that one. So we have, again, our disjunction, our first conditional on line 4, our second conditional on line 9, which on line 10 entitles us to write not Q, okay, by 1, 4, and 9, disjunction elimination. And we're done, right? Nope, we're not done because that's not what we're trying to prove. We got one more step, 11. If P, then not Q, 2 through 10, conditional introduction, and one big long line, 2 through 10. Okay, so that's a lot of practice, just combining disjunction elimination, conditional introduction, negation introduction. And that takes us halfway through this homework assignment, so I'm going to cut this in two since this is already pretty long, and we'll finish it up with another one.